No human-made machine was ever supposed to survive this close to the sun, but on Christmas Eve, 2024, while most of humanity was wrapping gifts and filling glasses and drifting off to sleep, a spacecraft the size of a small car crossed into the sun's atmosphere. Not near it, inside it. For days, no signal could reach it. Mission Control couldn't command it, check on it, or stop it. It was completely alone. When it came back, it carried answers to a question scientists had carried for 80 years. Why the sun's outer atmosphere burns millions of degrees hotter than its own surface. By the end of tonight, you will understand exactly how humanity touched a living star that changed solar science forever, what Parker Solar Probe found inside the sun, and what it reveals about the invisible forces already threatening every satellite, power grid, and modern way of life. Now get yourself comfortable, hit subscribe, we begin. For all of recorded history, the sun has been the one thing we were certain we understood. We have felt its warmth move through us every morning. We have built civilizations around its rhythm, measured the seasons by its arc, aimed every form of human worship toward its light. Of every object in the universe, this was the one we were most confident about. And yet, on December 24th, 2024, a spacecraft flew closer to the sun than any instrument in history, and what the data recorded near the solar atmosphere revealed something our best physics has struggled to explain for nearly a century. The more precisely science looks at our nearest star, the more it resists what we expect of it, and what Parker Solar Probe found when it finally got inside, deep inside, where the physics is actually happening, may be the most important solar data humanity has ever collected. December 24th, 2024 carried no pageantry, no cameras, no public countdown marking what was quietly occurring in the inner solar system. The world was largely occupied with ordinary things: holiday evenings, winter cold, the particular stillness of a night set apart from the rest. And in that same window of time, a machine roughly the size of a small car was executing the most extreme solar encounter in the history of spaceflight. Parker Solar Probe, named after astrophysicist Eugene Parker, a man who spent decades arguing for an idea most of his colleagues refused to accept, and who lived long enough to watch a spacecraft carrying his name launch into the sky in August of 2018. The probe carrying his name is modest in size. What it carried to the sun in terms of consequence was anything but. On that Christmas Eve, Parker reached its closest ever point to the sun, a distance of 3.8 million miles, roughly 6.1 million kilometers, from the solar surface. 3.8 million miles sounds vast by any measure familiar to daily life, but consider this. Mercury, the innermost planet in our solar system, orbits the sun at an average distance of 36 million miles, about 58 million kilometers. Parker's closest approach was nearly 10 times closer to the sun than Mercury's average orbit, and even at Mercury's nearest orbital point, the closest that planet ever gets to the sun, it still sits more than 7 times further away than Parker was during that pass. No instrument built by human hands had ever been that close to our star, and Parker was not drifting through that region. At its closest approach, the spacecraft was moving at approximately 430,000 miles per hour, about 692,000 kilometers per hour. Numbers at that scale need a frame to mean anything. To put that speed into human terms, at that velocity, Parker Solar Probe could travel from Philadelphia to Washington, D.C., a distance most people drive in 3 or 4 hours, in approximately 1 second. In a single heartbeat, it would cover a distance that takes a commercial airliner 45 minutes to cross. Parker Solar Probe was the fastest human-made object in the history of spaceflight, not by a narrow margin, decisively, and still moving at 430,000 miles per hour, buried inside the outer atmosphere of the sun. Parker was not skimming some thin boundary layer at the edge of space. The solar atmosphere is immense, The spacecraft was genuinely measurably inside it, collecting data where no instrument had ever taken readings from the inside. Here is the thing that should unsettle you slightly. Parker was not flying past the sun. Parker was flying through it, and then came the silence. The geometry of Parker's closest approach cut communication with Earth entirely, not partially, entirely. Mission control at the Johns Hopkins Applied Physics Laboratory could send nothing. No command would arrive before the moment had passed. No signal could return in time. No correction. No override. No instruction of any kind. Even at the speed of light, the absolute speed limit of the universe, a radio signal between Earth and the Sun travels for about 8 minutes in one direction. Any command sent from mission control at the moment of closest approach would arrive 16 minutes too late. Human reaction time simply does not apply at that scale. The machine was alone, flying on stored instructions, guided by autonomous systems built into its computers, protection logic designed to detect problems and respond without waiting for any direction from Earth. The engineers who built it had thought through every failure scenario they could imagine, written responses into the software, and then let go. That is what trust in engineering actually looks like, not confidence, letting go. And so the team that had spent 6 years guiding this machine toward this single moment sat down, watched the clock, and waited. For hours they had nothing. The spacecraft was intact, or it wasn't. It had survived, or it hadn't. They could not know. A beacon tone arrived late on December 26th, 2 full days after closest approach. Not a data stream, not a status report, a single short tone. The electronic equivalent of a hand raised in the dark to say, "Still here." The sound of a machine that had crossed through the atmosphere of a star and come out the other side. But what it had recorded in there, that was still coming. December 24th, 2024 was not Parker's first time inside the solar atmosphere. That is worth understanding, because it changes what the Christmas Eve pass actually means. On April 28, 2021, during its 8th orbit, Parker crossed a boundary that had never been crossed before. At about 8.1 million miles, roughly 13 million kilometers, from the solar surface. Scientists analyzing data from the spacecraft's instruments identified specific magnetic and particle signatures that could only mean one thing: the corona itself, measured from within. The crossing was announced publicly in December of 2021 at the American Geophysical Union meeting in New Orleans. For the first time in history, a human-made object had entered the sun's outer atmosphere. That moment was historic, but it was also only the beginning. The Christmas Eve pass went deeper, dramatically deeper. Each orbit since launch had drawn Parker progressively inward, tightened by 7 planned gravity assists from Venus, each flyby reshaping the trajectory a little further into solar territory. The final Venus flyby, in November of 2024, set the course for Christmas Eve. And Christmas Eve brought Parker closer to the solar surface than any previous pass, into conditions that no instrument in history had ever directly sampled. The data is still being extracted, but what scientists already know is extraordinary enough to demand attention. And to understand what it means, we need to go directly to the thing that makes the corona so fundamentally strange. The reason this mission was built in the first place. The sun's visible surface, the layer that produces the light we see from Earth, is called the photosphere. That is what you are seeing in any filtered solar image, a turbulent, churning field of luminous plasma. Plasma is a state of matter where extreme heat has stripped electrons completely free of their atomic nuclei, leaving a superheated, electrically charged gas that responds powerfully to magnetic fields. The photosphere burns at roughly 10,000 degrees Fahrenheit, about 5,500 degrees Celsius. That is hot enough to vaporize the most heat-resistant metal we know of in milliseconds. Above that surface sits the corona, the sun's outer atmosphere, a vast, diffuse envelope of charged particles extending millions of miles into the surrounding space, invisible to the naked eye under ordinary conditions. Only during a total solar eclipse does it reveal itself, appearing as a faint, ghostly halo around the moon's silhouette, wispy, almost quiet. But here is the thing, its temperature is not quiet at all. The corona reaches temperatures exceeding 1 million degrees Fahrenheit. In certain regions, several times higher than that, 200 times hotter than the photosphere sitting directly beneath it. Stand next to a fire, feel the heat. Step back, cooler. Step further, cooler still. This is not a casual observation about campfires. This is a foundational principle of physics. Heat radiates outward from its source. Energy dissipates with distance. Every heating process we have ever studied obeys this rule. The corona does not. The further you move from the sun's visible surface, the hotter its atmosphere becomes. Not in a localized region scientists might explain away. Not as a temporary anomaly. Consistently, dramatically, across the entire outer atmosphere. This should not be possible, and yet here it is, measured, confirmed, sitting at the center of solar physics, unresolved for nearly 90 years. Scientists call it the coronal heating problem. Astronomers first confirmed the temperature inversion in the 1930s, when Swedish physicist Bengt Edlen and German physicist Walter Grotrian identified spectral lines in coronal light that could only exist in gas heated to millions of degrees. The contradiction they revealed has never been fully explained. Theories exist, several serious ones. Magnetic waves may be carrying energy upward through the solar atmosphere and depositing it into the corona as they travel. Explosive events where magnetic field lines tangle, snap under the tension, and release stored energy in sudden violent bursts may be driving temperatures upward. Turbulence in the charged plasma of the solar atmosphere is almost certainly playing a role. Most likely several of these mechanisms are working together, but none has been confirmed as the primary cause. None. After 90 years. Parker Solar Probe was built in part to fly close enough to the corona to take the first direct measurements from inside the very environment where these processes are actually occurring. Not inferred from light crossing 93 million miles, not modelled from observations gathered at arm's length, from inside, where the physics is actually happening, where the answers have been waiting for instruments patient and durable enough to reach them. On December 24, 2024, it went deeper inside than any instrument had ever gone. Parker Solar Probe is not simply a camera pointed at the sun. 4 instrument suites operate simultaneously aboard it. One measures the electric and magnetic fields threading through the solar atmosphere. A second directly samples the charged particles, electrons, protons, helium nuclei, streaming outward from the sun. A third tracks energetic particles accelerated by solar activity. A fourth images the fine structure of the corona and solar wind, with cameras positioned closer to the solar surface than any imager has ever operated from inside. Together, they make Parker something we have never built before, a direct witness to the interior of a stellar atmosphere, not inferring from remote observation, not estimating from signals that have traveled 93 million miles and lost information along the way. Reading the environment the way a hand placed into a river tells you more about the current than any photograph taken from the bank ever could. Every measurement Parker sends back carries information from a place science had, for most of its history, only been able to describe from the outside. A small machine, alone between us and the star, translating proximity into understanding in ways no Earth-based telescope could replicate. And the fact that it survived long enough to send that understanding home is itself one of the most remarkable engineering stories in the history of spaceflight. Because reaching the sun, getting a machine to that distance at that speed, without it burning or breaking or drifting off course, is not simply a matter of building something tough enough. Getting there at all was never supposed to be easy. Why is the sun's outer atmosphere hotter than its surface? Scientists have pursued that question for nearly 90 years. Parker Solar Probe is now, for the first time, taking measurements from inside the corona itself, close enough to begin distinguishing between competing answers. What it has already found is shifting the models, changing what solar physicists thought they understood about how energy moves through our star's atmosphere. But this is not purely a scientific puzzle. What the sun stores in that atmosphere, it eventually releases. Charged particles, magnetized plasma, waves of energy flowing outward across the inner solar system toward every planet in their path, toward satellites in orbit, toward power grids running beneath our feet. The sun's reach does not end at its surface. Its atmosphere extends outward, invisibly, across hundreds of millions of miles. We are living inside it right now, and to understand what Parker found at the edge of that atmosphere, we need to understand something most of us were never fully told. The sun is not the calm, stable, well-understood star we have always assumed it to be. Its surface is not what we imagine. Its behavior is not what our models predicted, and the invisible environment it casts across the solar system is stranger and more consequential than almost anyone realizes. What it actually is, and what it actually does, is where the story gets genuinely unsettling. Most people carry a mental picture of the sun, a bright disk against a blue sky, warm light through a window in the morning, the steady, predictable arc from east to west that has structured human life for as long as human life has existed. For most purposes, that picture is enough. But that picture is not the sun. Not really. What we see from Earth is a simplified version, a projection of something far more violent, far more complex, and far more consequential than everyday experience allows us to appreciate. And the further science has looked beneath that familiar surface, the more the sun has resisted what we expected of it. Here is where it gets genuinely unsettling. The layer responsible for almost all the light reaching Earth, the part we actually see, is the photosphere. Think of it as the sun's outermost visible shell, the boundary from which light finally escapes into space after an almost unimaginable journey from the nuclear furnace at the sun's core. Every photon of sunlight that has ever warmed your face departed from this layer, a churning, granulated surface of luminous plasma, rolling and convecting like water boiling in an enormous pot, except the material is gas so energized that it has ceased to behave like anything we encounter in ordinary life. That surface burns at roughly 10,000 degrees Fahrenheit, about 5,500 degrees Celsius. For comparison, steel melts at approximately 2,700 degrees Fahrenheit. The photosphere is nearly 4 times hotter than that. A single square meter of the sun's surface radiates more energy per second than a large city consumes in an entire day. But the photosphere is only where the story begins. Above it, not below, but above, extending outward into the space surrounding the star, lies something that, when astronomers first measured its true properties, genuinely made them question whether their instruments had failed. The corona is the sun's outer atmosphere. Under ordinary conditions, it cannot be seen at all, overwhelmed entirely by the brilliance of the photosphere below it. Only during a total solar eclipse, when the moon slides precisely between Earth and the sun and blocks the photosphere completely, does the corona reveal itself, and when it does, it appears as a ghostly silver halo, wispy, flowing, extending outward in long, delicate streamers that can reach for millions of miles in every direction. Its appearance suggests something quiet, something thin and insubstantial. But here is the problem. The corona is filled with plasma, gas so superheated that its electrons have been torn completely free of their atoms leaving behind a fluid of charged particles that behaves nothing like the gas or liquid or solid we know. This plasma is not passive. It is threaded through by magnetic fields generated deep inside the Sun, fields so powerful and so constantly shifting that understanding their behavior has occupied solar physicists for the better part of a century. And now, the central fact. The fact that should not be possible, but is. The corona reaches temperatures of at least 1 million degrees Fahrenheit. In certain active regions, measurements suggest temperatures several times that. The outer atmosphere of the Sun, the layer farthest from its energy source, is roughly 200 times hotter than the visible surface directly beneath it. Moving away from the heat source, the temperature does not decrease, it explodes upward. Let's be precise about when this was confirmed, because it matters. Swedish physicist Bengt Edlund and German physicist Walter Grotrian identified the corona's extreme temperature in the 1930s, not by visiting it, but by analyzing the specific wavelengths of light the corona emitted. Those wavelengths, called spectral lines, could only be produced by gas heated to millions of degrees. Before that discovery, astronomers assumed the corona was relatively cool, a thin, unremarkable fringe above the solar surface. The spectral data said otherwise, dramatically otherwise. Scientists named the contradiction the coronal heating problem, and for nearly 90 years since it has remained one of the most embarrassingly persistent unsolved mysteries in astrophysics. Not for lack of effort, not for lack of intelligence applied to it. The problem has endured because the Sun, examined closely, refuses to behave the way our models demand. But here is what makes the mystery even stranger. Scientists are not in the dark about possible explanations. They have several, and the difficulty is not that none of them work, it is that more than one of them might be right, and separating their contributions has proven extraordinarily difficult from the distances at which instruments have historically operated. Let's talk about what those mechanisms actually are. The most prominent explanation involves the Sun's magnetic field acting as an energy carrier. Deep inside the solar interior, churning plasma generates a magnetic field of almost incomprehensible complexity. That field extends upward through the photosphere and into the corona, threading through the atmosphere in constantly moving loops, arcs, and filaments. One theory holds that disturbances in this field generate what physicists call Alfvén waves, waves that travel along magnetic field lines, the way vibration travels down a plucked guitar string, carrying energy without carrying mass. As those waves propagate upward into the corona, they dissipate, releasing their energy as heat into the surrounding plasma. Observations from multiple space missions have confirmed that Alfvén waves exist in the corona. They are real. The debate is whether they carry sufficient energy to account for the full scale of the heating. A second mechanism is magnetic reconnection. Imagine two magnetic field lines pushed toward each other by the constant motion of solar plasma. When they meet with enough force, they snap, breaking apart and instantly reconnecting in a new configuration, releasing stored magnetic energy as an explosive burst of heat and particle acceleration. The process is real, observed, and documentable. During solar flares, the most powerful explosions in the solar system, magnetic reconnection is the dominant energy source. Whether it operates on a smaller, more continuous scale throughout the corona, depositing energy steadily enough to sustain the million-degree temperatures remains under active investigation. And turbulence. The corona is not a smooth laminar medium. The plasma flowing through it is inherently turbulent, churning on scales too small for distant telescopes to resolve. Turbulent energy dissipates as heat. How much heat and where is a question that requires measurements taken from inside the corona itself, not from 93 million miles away. Here is what makes this genuinely unsettling. All three mechanisms are probably contributing. The science is not a clean debate between two competing theories where one will eventually win. The reality appears to be messier than that, a mixture of processes interacting with each other, varying across different regions of the corona, shifting with the sun's 11-year activity cycle. Disentangling them requires data that, until Parker Solar Probe, simply did not exist. But here is the moment where the coronal heating problem transforms from a distant scientific puzzle into something that concerns the world you actually live in. The corona is not simply a strange hot layer sitting passively above the solar surface. The corona is where the solar wind is born. The solar wind is a continuous, unrelenting stream of charged particles, mostly electrons and protons, that the sun releases in all directions every second without pause. At the corona's extraordinary temperatures, the sun's own gravity cannot fully hold the outermost layer of its atmosphere. The plasma is too energized, too fast, too determined to escape, and so it does. It flows outward into interplanetary space at speeds ranging from about 250 miles, 400 kilometers per second to 500 miles, 800 kilometers per second. On the slow end, that is roughly 1 million miles per hour. During intense solar activity, it moves faster. Think about what that means for a moment. The sun is not sitting quietly in the middle of the solar system. The sun is continuously exhaling, casting a river of charged, magnetized material outward in every direction, filling the entire volume of space surrounding the planets with a thin but relentless stream of solar material. Scientists call the region filled by this stream the heliosphere, the vast bubble of solar influence that surrounds the entire solar system. The heliosphere extends outward roughly 120 times the Earth-Sun distance. That is so far that Pluto, at the outermost edge of what most people think of as the solar system, remains well inside this bubble. The Voyager spacecraft, launched in 1977 and traveling continuously at more than 35,000 miles, 56,000 kilometers per hour, only crossed the heliosphere's outer boundary in 2012, 35 years of flight, and Earth sits near the inner edge of it. We are not observing the sun from outside its sphere of influence. We are living inside it. Here is what most people misunderstand about the sun's relationship to modern civilization. When most people think of the sun's influence, they think of light, warmth, the energy that drives weather and photosynthesis, and the visibility of everything around them. Those effects are real and vast, but there is an invisible layer of solar influence that operates entirely outside of light, and it reaches directly into the infrastructure that sustains contemporary life. When a powerful solar eruption occurs, a coronal mass ejection, the sudden violent expulsion of billions of tons of magnetized plasma from the corona, that material crosses interplanetary space and collides with Earth's magnetic field. The collision induces enormous electrical currents in anything long and conductive enough to act as an antenna. Long-distance power transmission lines, pipelines, communication cables laid across continents. On March 13th, 1989, one such ejection struck Earth. The event is documented, measured, and studied to this day. The storm cloud from the sun traveled at approximately 1 million miles per hour. It hit Earth's magnetic field, and then the cascade began. The power grid serving the entire province of Quebec, Canada, delivering electricity to millions of people in the final cold weeks of winter, collapsed. 6 million people lost power. The blackout lasted more than 9 hours, and the grid failed in less than 90 seconds from the moment the storm arrived. Hydro-Quebec, the province's electricity utility, subsequently spent $2 billion over 6 years hardening its systems against future solar events. What the sun's atmosphere released in a matter of hours cost $2 billion and years of engineering to guard against. That 1989 storm was a moderate one by historical standards. Satellites in orbit are continuously exposed to solar wind particles that erode electronics, degrade sensors, and shorten operational lifespans. The GPS signals embedded in smartphones, aircraft navigation systems, and emergency vehicles travel through the same disturbed environment. Aviation communications over polar routes can be severed entirely during intense events. NASA and other space agencies now operate dedicated space weather forecasting programs, continuous monitoring operations designed to track what the sun is doing, because what the sun does reaches Earth in ways that have nothing to do with sunlight. The auroras visible above the polar regions, perhaps the most breathtaking natural light display on Earth, are the sun's charged particles colliding with atmospheric molecules dozens of miles overhead. Every aurora you have ever seen, or seen in photographs, is a piece of the sun reaching the top of our sky. The sun's atmosphere becomes Earth's weather, not metaphorically, physically. Parker Solar Probe was not built out of abstract curiosity. Understanding the corona and understanding what drives the solar wind close to its source, rather than 93 million miles downstream, has direct and measurable consequences for every forecasting model, every satellite in orbit, every power grid built at latitudes where solar storms hit hardest. But here is what sits underneath all of it, a question that must be answered before any of this mission's discoveries can be fully appreciated. How did scientists even know the solar wind existed? Before any spacecraft had left Earth, before any instrument had flown close enough to the sun to detect it, decades before Parker Solar Probe was conceived, a single scientist sat down, did the mathematics, and concluded that the sun must be continuously exhaling material into interplanetary space. His colleagues considered the idea embarrassing. The leading scientific journal of the time refused to publish it. He was right, and the story of how one rejected idea eventually became the theoretical foundation of an entire field and a mission is one of the most important and most overlooked episodes in the history of modern science. His name was Eugene Parker. He was 30 years old. He had just submitted a paper to one of the most prestigious scientific journals in the world, a paper containing mathematics that no one had found fault with, describing a phenomenon that no one had directly observed, predicting the existence of something the scientific establishment was certain could not exist. The reviewers who read it were furious, and yet everything he wrote turned out to be correct. The story of how Parker Solar Probe came to exist, how a mission bearing one man's name came to fly inside the atmosphere of a star, begins not with a rocket or a heat shield or a NASA budget approval. It begins in 1958 in a university office in Chicago with a young physicist, a piece of mathematics, and the kind of silence that follows when an idea arrives before the world is ready for it. Eugene Parker was not studying the sun's surface when the idea came to him. He was thinking about something much simpler. He was thinking about comets. Comets have tails. Everyone knows this. They stream behind the comet as it moves through space, glowing in the darkness. But here is the thing that troubled Parker, and had troubled astronomers for some time before him. Comet tails do not stream behind the comet. Not exactly. They always point away from the sun, regardless of which direction the comet is actually traveling. When a comet approaches the sun, its tail trails behind it, away from the sun. When a comet moves away from the sun, its tail points in the same direction it came from, still away from the sun. Always away. Without exception. Something was pushing those tails, something flowing outward from the sun in all directions, continuously, with enough force to deflect the tenuous material of a comet's tail across millions of miles of interplanetary space. A German astronomer named Ludwig Biermann had noted this in the 1950s and proposed the idea of what he called corpuscular radiation, a stream of particles from the sun. A British astrophysicist named Sidney Chapman had separately shown that the sun's corona must extend far into space and remain extraordinarily hot at great distances. Parker looked at both ideas together. He sat down with the mathematics, and what the equations told him was stark. The corona was so hot, so impossibly energetic, that the sun's own gravity could not hold it. The outermost layer of the solar atmosphere had to be escaping continuously, flowing outward into interplanetary space at supersonic speeds. Not in bursts, not occasionally, always. A permanent, relentless outflow of charged particles filling the entire solar system and beyond. Parker called it the solar wind. In 1958, Parker submitted a paper titled Dynamics of the Interplanetary Gas and Magnetic Fields to the Astrophysical Journal. He laid out his mathematics clearly. He showed his reasoning. He made specific, testable predictions about the speed of the solar wind, its structure, and the shape it would impose on the sun's magnetic field across the solar system. Then he waited. The response, when it came, was not what a scientist hopes for. Two anonymous reviewers, both regarded as experts in the field, rejected the paper, not because they found mathematical errors. They looked for errors and did not find them. The rejection was something closer to disbelief. One reviewer's comments survive in historical record. The message, according to Parker himself, amounted to this: before attempting to write a scientific paper, you should go to the library and actually read about the subject. Think about that for a moment. An idea containing no demonstrable errors, rejected not on the basis of its logic, but on the basis that it conflicted with what the reviewers already believed to be true. But here is where the story turns. Subrahmanyan Chandrasekhar was the editor of the Astrophysical Journal. He was already one of the most distinguished astrophysicists in the world, a man who would go on to win the Nobel Prize in Physics in 1983, and whose name the Chandra X-ray Observatory now carries into orbit above Earth. Chandrasekhar read Parker's paper himself. He could not find the errors either. The mathematics were sound. The logic was coherent. The prediction was extraordinary, but it was not irrational. Chandrasekhar overruled the reviewers. He published the paper, and the scientific community largely ignored it anyway. Here is the paradox that makes Parker's story genuinely unsettling for anyone who cares about how science actually works. The scientific consensus of the late 1950s held that interplanetary space was essentially quiet, a near vacuum threaded by weak magnetic fields, largely undisturbed between the planets. The space between Earth and the Sun was imagined as empty in a way that was comfortable, a void, not an ocean. Parker's solar wind demolished that picture entirely. No one's instruments had measured it. No satellite had detected it. The prediction rested entirely on mathematics and reasoning from known facts about the corona's temperature. And the established experts, the people most qualified to evaluate the claim, looked at it and said, "Impossible. The sun does not work that way. You are wrong." The mathematics said otherwise. The mathematics were clear, and no one could explain why they were wrong, not even the people who rejected them. That is the moment, not in a laboratory, not at a launch pad, but in a peer review process in 1958, where the foundation of one of the most important space science missions in history was quietly laid. The vindication did not come from a calculation. It came from a machine traveling through space. In 1959, the Soviet satellite Luna 2 captured preliminary hints of particle streams in the interplanetary environment. Scientists noticed, but the measurements were ambiguous enough that the debate continued. 3 years later, in 1962, NASA's Mariner 2 spacecraft was traveling toward Venus when its instruments detected something unmistakable: a continuous, supersonic stream of charged particles flowing outward from the Sun. Mariner 2 confirmed the solar wind's existence directly, measuring speeds that matched Parker's predictions. The instrument that co-designed those measurements was partly the work of Marcia Neugebauer at NASA's Jet Propulsion Laboratory, a scientist whose careful data removed any remaining ambiguity. The solar wind was real. Parker had been right. The reviewers who told him to go to the library had been wrong. Not slightly wrong, fundamentally, completely wrong. What followed Parker's vindication was not a slow, grudging correction. the field transformed. Heliophysics, the scientific discipline dedicated to understanding the Sun and its influence on the solar system, grew into a major branch of modern astrophysics, built substantially on the conceptual framework Parker had established in that rejected paper. Multiple phenomena in solar and plasma physics now bear his name: the Parker spiral, the Parker instability, the Parker equation. The language of solar science, woven through with his ideas, is the language a young physicist learns on the first day of graduate study in the field. A 1960 Space Science Board report, prepared just 2 years after his paper was published and before Mariner 2 had confirmed the solar wind, had already recommended a dedicated solar probe to investigate the origins of Parker's solar wind. The idea for the mission existed before the concept it was meant to study had even been confirmed. That is how far ahead Parker's thinking had run. NASA had named spacecraft after many things, telescopes after great astronomers long dead, observatories honouring figures from centuries past. The tradition of naming missions for scientists was always retrospective, honouring the work of those who could no longer see what their ideas had eventually produced. Parker Solar Probe broke that tradition. On May 31, 2017, NASA announced that the mission would carry the name of Eugene Parker, the first time in the agency's history that a spacecraft had been named for a living person. Parker was 90 years old. He was emeritus professor at the University of Chicago, the same institution where he had spent most of his career. He still went to his office. He still engaged with the literature. And he was, by all accounts, genuinely surprised that the honour had found him. He inscribed the mission patch by hand. What he wrote on it was entirely characteristic. "This mission is hot stuff." Then came the morning of August 12, 2018. Parker was 91 years old. He stood at Cape Canaveral with 3 generations of his family, children, grandchildren, all gathered to watch a Delta IV heavy rocket lift a spacecraft bearing his name into a dark pre-dawn Florida sky. He had never, in all his decades of scientific life, watched a NASA launch in person. At 3:31 in the morning, the rocket ignited. "Here we go," Parker said quietly as it rose. He watched it climb through the clouds, growing smaller, until the light of its engines was indistinguishable from the stars it was heading toward. Later, he would describe the moment with the same calm economy that had always characterized his work. "So much has gone into this launch," he said, and then to see it all disappear slowly, fading away into the night sky, knowing it will never come back. It was a moving experience. A 60-year journey from a rejected paper to a spacecraft flying into the sun's atmosphere, compressed into a few minutes of Florida darkness. Eugene Parker died on March 15, 2022, at the age of 94. By then, Parker Solar Probe had already made multiple passes through the solar corona. His namesake machine had already entered the very atmosphere whose existence he predicted, taking measurements from a place he had described in mathematics before any instrument in history had reached it. He had lived long enough to see the data. The mission had not finished its work. But the question Parker first asked in 1958, "Why does the solar wind exist, and where exactly does it begin?" was finally being answered from inside. Science moves in a particular direction when it works at its best. From theory to instrument to evidence. An idea precedes the technology to test it. The technology waits for the engineering to make it possible, and the engineering waits for a question urgent enough to justify the attempt. Parker's 1958 paper was the idea. Mariner 2 was the first crewed instrument, and Parker Solar Probe, 60 years later, is the technology that finally reached the place the mathematics pointed toward all along. But reaching the corona requires more than patience. The problem is not the distance. The problem is not the speed. The problem is not the communications or the trajectory or the orbital mechanics. Though all of those presented challenges that took decades to solve, the most fundamental problem, the one that makes a mission like Parker Solar Probe seem barely credible even today, is simpler and more brutal than any of that. How do you build a machine that survives inside a star? The corona that Parker predicted, the corona his spacecraft is now flying through, reaches temperatures exceeding 1 million degrees Fahrenheit. The sun's radiation at that distance is powerful enough to vaporize most materials in seconds, and the spacecraft cannot simply park at a safe distance and observe. To take the measurements that actually distinguish between competing theories of coronal heating and solar wind acceleration, it has to go in, all the way in. The engineering that made that possible is one of the most extraordinary stories in the history of spacecraft design, and it begins with a single question that sounds almost impossibly simple. How do you keep something cool a few feet from a million-degree fire? The engineers who designed Parker Solar Probe knew something that might seem, at first, like it should make the problem easier. The corona, that million-degree outer atmosphere the spacecraft would be flying through, is extraordinarily thin. Almost nothing is out there. Far fewer particles per cubic inch than in the best vacuum chamber ever built in a laboratory on Earth. And yet the sun, at the distance Parker travels, delivers more than 500 times the solar energy that reaches Earth, enough to reduce most materials to vapor within seconds, enough to blind instruments, enough to overwhelm any cooling system built by conventional means. The question was not simply, how hot will Parker get? The question was, how do you design a machine to survive inside a stellar environment when the threats arriving at it are fundamentally different from anything engineers had designed against before? The answer required a heat shield that should not work as well as it does, and it is one of the most quietly extraordinary pieces of engineering in the history of spaceflight. The component standing between Parker Solar Probe and total destruction is called the Thermal Protection System, or TPS. At first glance, the description sounds almost absurdly modest. A circular disc, 8 feet, 2.4 meters in diameter, 4.5 inches, about 11.5 centimeters, thick, weighing approximately 160 pounds, roughly the weight of an average adult human being. That is the entire shield, 8 feet wide, 160 pounds, between a spacecraft and the outer atmosphere of a star. But what that shield is made of and how it is constructed is where the engineering becomes genuinely remarkable. The outer faces of the TPS are made from carbon-carbon composite, a material formed by taking carbon fiber and embedding it in a carbon matrix under extreme heat, producing a structure that is simultaneously very strong and extraordinarily heat-resistant. Each outer face is less than 1/10 of an inch thick, thin enough, in fact, to be slightly flexible if you tried to bend it by hand. But what gives the shield its structural integrity is what sits between those two thin faces, a core of carbon foam, 4.5 inches deep, that is 97% air. 97% air. Think about what that means physically. Carbon is a conductor of heat, but carbon foam is almost entirely empty space. The heat trying to travel through the shield from the sun-facing side encounters almost no material to conduct through. Solid carbon would transfer heat efficiently. Foam carbon, riddled with tiny voids, transfers almost nothing. The same principle underlies why an oven mitt can protect your hand in a 400-degree oven. The trapped air inside the insulating material has nowhere to carry the heat quickly enough to reach your skin. The carbon foam operates on the same logic, scaled to extreme temperatures. The sun-facing side of the TPS is also coated in a white ceramic paint, a specially formulated reflective layer designed to bounce as much of the sun's incoming radiation away from the shield as possible. Reflection first, then insulation through the foam, then the shadow. And in that shadow, everything changes. At Parker Solar Probe's closest approach to the sun, the temperature on the sun-facing surface of the heat shield reaches approximately 2,500 degrees Fahrenheit, about 1,370 degrees Celsius. Hotter than lava, hot enough to melt iron, hot enough to vaporize most metals used in engineering. On the other side of those 4.5 inches of foam, the spacecraft's instruments and systems operate at approximately 85 degrees Fahrenheit, about 30 degrees Celsius, the temperature of a warm day. 4.5 inches of foam separates 2,500 degrees from 85. But here is what makes that possible, and what makes the shield more than just insulation. The TPS attaches to the spacecraft's body at only 6 points, 6 carefully designed connection points, engineered to minimize the surface area through which heat can travel from the shield into the spacecraft structure by conduction. The shield floats in front of the spacecraft, not pressed against it, not fused to it, connected at the minimum number of contact points physically required to hold it in place. And behind the shield, everything must stay in its shadow. Every instrument, every component, every wire and sensor and camera on the spacecraft must remain within the cone of shade the TPS casts as it faces the sun. The moment any part of Parker drifts outside that shadow, even briefly, even partially, the consequences are severe. The solar radiation at that distance would reach an unprotected surface almost immediately and begin degrading it. This is not a theoretical risk. The geometry of protection requires precision that human operators cannot provide in real time. The speed at which Parker Solar Probe crosses through the solar environment near perihelion, 430,000 miles per hour, makes it physically impossible for human controllers on Earth to respond to any threat quickly enough to matter. At Parker's closest approach, the spacecraft is still tens of millions of miles from Earth. A radio signal traveling at the speed of light takes several minutes to cross that distance in one direction. Any command sent from mission control at the moment a problem began would arrive, at the absolute minimum, minutes after the situation had already resolved itself one way or another. A few minutes, at 430,000 miles per hour, is an eternity of exposure. So Parker does not wait for human instructions near the sun. The spacecraft operates on an onboard autonomous guidance and control system that continuously monitors the spacecraft's orientation, compares it against the required pointing angle to keep all instruments inside the TPS shadow, and corrects any deviation automatically immediately without waiting for any signal from Earth. This autonomy extends to the solar arrays. The solar panels that generate Parker's electrical power present their own engineering paradox. They must face the sun to generate electricity, but the closer to the sun the spacecraft travels, the more intense the sunlight becomes, and solar panels are sensitive to overheating. Too much heat degrades their efficiency and eventually destroys them. The arrays are mounted on adjustable wings, and autonomous software tilts them to precisely the right angle at each distance from the sun, catching enough sunlight to generate power while angling away enough to avoid overheating. To go further, Parker uses a first-of-its-kind water-cooled solar array system. Water flows through miniature channels embedded within the solar array panels, absorbing heat, then circulates to 4 radiator panels positioned in the shadow of the TPS. Those radiators face cold open space and shed the absorbed heat outward. It is the same principle as a car's radiator. Absorb heat from where it accumulates, carry it somewhere it can dissipate, release it to the environment. Except the environment is deep space, and the system must operate without a single human adjustment for days at a time near the sun. And here is what makes the whole arrangement so unsettling when you think about it carefully. At any moment during a solar encounter, Parker Solar Probe is performing dozens of simultaneous autonomous calculations, monitoring orientation, correcting pointing, tilting the arrays, circulating coolant, managing power, protecting instruments, responding to sensor readings, all of it alone, in real time, inside the outer atmosphere of a star, with no human able to intervene quickly enough to make a difference if something went wrong. The engineers who built it understood that this was what the mission required. They had to trust the machine with its own survival, and with humanity's only opportunity to take measurements from inside the corona. But here is the part of the engineering story that most people do not expect. The corona, the million-degree environment Parker Solar Probe flies through, is not the primary thermal threat to the spacecraft. To understand why, we need to separate two ideas that our instincts tend to blend together: temperature and heat transfer. Temperature measures how fast individual particles are moving. Heat transfer measures how much energy those particles actually deposit into something they touch. A particle moving extremely fast carries a great deal of energy per particle. But if there are very few particles, if the environment is extremely thin, almost empty, then the total energy deposited remains small because there are so few collisions happening. Picture this: an oven set to 400 degrees Fahrenheit. The air inside the oven is hot, but you can reach your arm into that oven for a short time without immediate harm. Now picture a pot of boiling water at 212 degrees, less than half the temperature of the oven. But the moment your skin makes contact with that water, the burn is nearly instantaneous. Dense material transfers heat far more efficiently than diffuse material, even when the diffuse material is technically hotter. The corona operates on this same principle. The particles in the corona, electrons, protons, and helium nuclei, are screaming through space at temperatures of millions of degrees. But the corona is extraordinarily diffuse. At the distances Parker Solar Probe travels, the density of coronal material is so vanishingly thin that the actual rate of energy deposition into the spacecraft from those particles is minimal. The corona touches Parker. It does not scald it. What actually threatens Parker Solar Probe is the sun's electromagnetic radiation, the light and heat radiating from the photosphere directly at 500 times the intensity that reaches Earth. That is what the heat shield is designed to handle, not the coronal plasma, the photons. The shield reflects what it can. The foam absorbs and blocks what remains. The shadow protects everything behind it. The radiators shed the heat generated by the solar arrays, and the autonomous systems maintain the geometry that holds it all together. The spacecraft's survival does not rest on any single element of this design. Pull out any one layer, remove the white coating, eliminate the foam, delete the autonomous pointing control, disable the water cooling, and the system fails. Every component depends on every other component. The engineering is not a series of independent solutions. It is one integrated defense, operating simultaneously in a place no machine has survived before. The remarkable fact, the fact that makes all of this engineering matter, is that Parker's instruments are not merely surviving inside the corona. They are working, measuring, recording, sampling the magnetic fields and particle populations and wave structures of a stellar atmosphere from the inside in real time, at a level of detail no remote observation could ever replicate. Every reading the instruments take happens because the shield is doing its job, because the foam is holding the temperature differential across 4.5 inches, because the autonomous system is keeping every sensor inside the shadow, because the water is circulating through the solar array panels and the heat is bleeding off into cold space through the radiators. The science and the engineering are not separate endeavors here. They are the same endeavor. Parker Solar Probe can only answer the questions Eugene Parker asked in 1958 because the engineers at the Johns Hopkins Applied Physics Laboratory found a way to keep a machine alive in the place those questions pointed toward. A 160-pound shield made mostly of air, carrying instruments through the atmosphere of a star, operating on its own, sending data home. But surviving inside the corona required more than a heat shield. Getting there in the first place required solving a problem so counterintuitive that it surprises almost everyone who encounters it for the first time. The sun is not far. By cosmic standards, it sits almost at our doorstep, 93 million miles, about 150 million kilometers away. And it is not small. a target so large that even rough aiming should bring a spacecraft close enough to study it from a useful distance. So, here is the question that should be nagging at you. If the engineering problem of surviving near the Sun took decades to solve, if it required carbon foam and water cooling and autonomous software and white ceramic paint and 6 carefully chosen attachment points, what was the problem with simply pointing a spacecraft toward the Sun and launching it? Why, in 60 years of spaceflight, did it take until 2018 to send the first mission into the corona? The answer has nothing to do with heat, nothing to do with radiation, nothing to do with material science or engineering restraint. The obstacle was something far more fundamental, something embedded in the physics of how every object in the solar system moves. Getting a spacecraft to the Sun turns out to be one of the hardest journeys in the solar system to make, not because of the destination, because of where we start from, and understanding why requires understanding something about motion that most people have never been told. Most people, if asked, would assume that reaching the Sun is the easiest journey in the solar system. It is enormous. It is close. Its gravity pulls every object in the solar system toward it, constantly. Surely, the logic goes, reaching the Sun requires nothing more than pointing a spacecraft in the right direction and letting gravity do the rest. But here is the problem. That logic is completely wrong. Getting a spacecraft close to the Sun is not just difficult. By one measure, it is harder than reaching the edge of the solar system entirely. It requires more energy than a mission to Pluto, more energy than the Voyager probes needed to escape the solar system altogether, and it cannot be done in a straight line. The reason has nothing to do with heat, nothing to do with the shield or the autonomy systems or any of the engineering challenges we have already explored. The obstacle is something that acts on every object launched from Earth, invisibly perpetually from the moment of liftoff, and understanding it requires stepping back from space entirely and looking at how Earth itself moves. Right now, as you sit still, you are moving, not rotating with Earth, though that too, but travelling in a vast ellipse around the Sun at approximately 67,000 miles per hour, about 107,000 kilometers per hour. That is Earth's orbital speed, the speed at which our planet sweeps through its orbit around the star at the center of the solar system, 67,000 miles per hour. To cross the full width of the continental United States at that speed would take less than 2.5 minutes. And here is the critical fact. Every spacecraft launched from Earth inherits that velocity the moment it leaves the ground. Not partially, entirely. A rocket lifts a spacecraft off the surface and sends it into space, but the rocket cannot cancel out the 67,000 miles per hour that the spacecraft already possesses simply by being on a planet moving through the solar system. That sideways velocity is baked into the mission from the first second of launch. This is not a problem when heading outward, to Mars, Jupiter, or beyond. A spacecraft aimed outward is already moving in roughly the right direction. Adding velocity in the direction of travel is achievable, but to fall toward the Sun, to move inward, to reduce the orbital radius, to stop sweeping sideways at 67,000 miles per hour and begin falling straight in, the spacecraft must shed that orbital velocity. It must slow down sideways, and slowing something down in space where there is no air resistance to help, no brakes to press, nothing to push against, requires either enormous fuel expenditure or an extraordinarily clever alternative. Let's put this in perspective. NASA engineers calculated that reaching the Sun directly, cancelling the orbital velocity inherited from Earth sufficiently to fall into a close solar orbit, would require more energy than any rocket ever built could provide for a mission of Parker Solar Probe's size and mass. The energy required to get close to the Sun is roughly 55 times greater than the energy needed to reach Mars. Not 55% more, 55 times more. Think about what that means. Mars sits hundreds of millions of miles away, in a different part of the solar system, often in a completely different direction. and reaching Mars from Earth is still far easier than moving a spacecraft significantly inward from Earth's orbit toward the Sun. The reason is orbital mechanics, the physics of how objects move under gravity in space. In any orbit, speed and altitude are linked. Move faster, and gravity curves your path into a larger orbit, pushing you outward. Slow down, and gravity pulls your path into a smaller orbit, drawing you inward. To get significantly closer to the Sun, Parker Solar Probe needed to shed an enormous amount of its inherited sideways speed. No fuel supply carried on a spacecraft could accomplish that alone. The numbers simply do not permit it. But here is the thing about orbital mechanics. The same physics that makes direct trajectories to the Sun nearly impossible also offers an elegant alternative, one that uses gravity itself, not fuel, to reshape a spacecraft's orbit over time. The solution the mission designers found was planetary gravity assists. A gravity assist, sometimes called a gravitational slingshot, is not quite what the name implies. The name makes it sound like an acceleration, a planet catching a spacecraft and flinging it somewhere. That is the common perception, but the underlying physics is more precise and in some ways more interesting than a simple slingshot. When a spacecraft passes close to a planet, the planet's gravity bends the spacecraft's path. The geometry of that bend, how closely the spacecraft approaches, from which direction, at which angle, determines exactly how the spacecraft's speed and trajectory change relative to the Sun. A gravity assist can speed a spacecraft up or slow it down, depending entirely on how the approach is designed. For Parker Solar Probe, the mission designers needed to slow the spacecraft down, not speed it up. They needed a planet whose gravity could curve Parker's path in a way that removed orbital energy, tightening the orbit around the Sun with each pass. And the planet they chose was not Jupiter, the most massive option, or Mars, the most commonly visited. They chose Venus. Venus sits in precisely the right location in the inner solar system, between Earth and the Sun, and its gravity, when used correctly, can act like a hand pressed against the spacecraft's path, redirecting its trajectory progressively inward. Each Venus flyby would remove a portion of Parker's orbital energy, tightening the loop it drew around the Sun, bringing each successive perihelion, each closest approach, a little bit deeper into solar territory. 7 flybys, over nearly 7 years. The first Venus flyby occurred just 52 days after launch, October 2018. Parker used Venus's gravity to break the previous record for the closest human-made object to the Sun, surpassing Helios 2, which had held that record since 1976. But the orbit at that stage was still relatively wide. Venus had only begun the work. Each subsequent flyby arrived at a different point in Parker's long, narrowing elliptical path around the Sun. The second in December 2019, the third in July 2020, the fourth and fifth, the sixth. Each time, Venus's gravity bent the orbit a little tighter, pushed the perihelion a little closer to the solar surface. Each time, Parker broke its own previous record for closest approach. The engineering required to time these flybys was extraordinary. The 7 passes were not independent maneuvers that could be adjusted freely. They formed a chain in which each flyby had to hit a precise target so that the next flyby would arrive at Venus at exactly the right position. Miss the aim point at one flyby by even a small margin, and the chain broke. Parker would miss subsequent opportunities, potentially derailing years of trajectory work. And here is the thing most people misunderstand about the final flyby. On November 6, 2024, Parker Solar Probe made its 7th and last pass of Venus. The spacecraft swept within 240 miles, about 387 kilometers, of Venus's surface. For comparison, most commercial aircraft fly at cruising altitudes around 6 or 7 miles above Earth's surface. Parker passed Venus at roughly 40 times that height, extraordinarily close for a spacecraft in interplanetary space, navigating at tens of thousands of miles per hour. That seventh pass was not an acceleration. It was, as all the Venus flybys before it had been, a controlled reduction, a precise removal of orbital energy, executed with gravitational geometry rather than fuel, and it locked Parker onto its final course. The paradox here is one of the most quietly extraordinary things in the whole story of this mission. To reach the Sun, to fall inward, toward the most massive object in the solar system, the object whose gravity dominates everything within billions of miles, Parker Solar Probe had to first fly outward. It launched on a trajectory that took it away from Earth and toward Venus. It then used Venus 7 times to gradually remove the sideways velocity it had inherited from Earth. Only by repeatedly borrowing Venus's gravity, using one planet's pull to reshape its relationship with another planet's star, could Parker achieve the trajectory its scientific mission required. You cannot reach the Sun by aiming at it and firing a rocket. You cannot reach the Sun by letting gravity pull you in. You reach the Sun the way Parker reached it, by borrowing patience, borrowing precision, and borrowing the gravity of another world across 7 years and 7 flybys. Each orbit was a smaller loop, each perihelion closer. December 24th, 2024 was not the first close approach Parker made to the Sun. It was simply the deepest, the result of a sequence of increasingly extreme passes that had been building since launch. Like a stone swung on a shortening string, each revolution tighter than the last, until the string reached its minimum length and the stone arrived at its closest possible point. But the trajectory engineers had designed a mission to the Sun. What they had not fully planned for initially was that Venus itself would offer scientific returns. The original mission plan included Venus as a navigation tool only, a gravitational waypoint, not a scientific target. But shortly after launch, as Parker's instruments proved more capable than anticipated, the mission team revised that approach. Each Venus flyby became an opportunity. During its 4th Venus flyby, Parker's wide-field imager, its camera designed to photograph the solar corona, captured something remarkable: the first direct images of the night-side surface of Venus through its cloud layers, not its day side, which reflects sunlight, the actual surface, seen through an infrared glow, glowing with its own thermal emission. A planet revealing itself to a spacecraft that had come to borrow its gravity. Venus, in a real sense, gave Parker Solar Probe more than a trajectory. It gave heliophysics scientists unexpected data about a world they were only passing through. The gravity assist and the scientific observation arrived in the same flyby, from the same instruments, on the same spacecraft. And with the 7th pass complete, Venus had done everything it could. Parker was now aimed where no spacecraft had aimed before. 7 years of narrowing loops, 7 Venus flybys, 24 orbits around the Sun, each one gathering data as Parker swept inward through the corona, approached perihelion, and swung back out to begin the next loop. By the time Parker reached the Christmas Eve 2024 encounter, it was not arriving at the Sun for the first time. It had been studying the corona for years, from progressively closer vantage points, with instruments recording the particle populations, the magnetic fields, the wave structures, the energetic events of the solar atmosphere with a clarity no mission had ever achieved. And what it had already found in those earlier passes, before the record-breaking December approach, had already begun to unsettle the models. Because here is what no one anticipated: the solar corona, the environment Parker had been flying through since April 2021, behaved differently up close than the models predicted. Not slightly differently, significantly differently. The data contained structures, events, reversals, and patterns that existing theories had not prepared solar physicists to see. And the closer Parker flew, the stranger the corona revealed itself to be. The data from Parker Solar Probe's first solar encounters arrived at the Johns Hopkins Applied Physics Laboratory in late November 2018. Scientists had been waiting months for it. They had spent years building the instruments that collected it. They had been refining their models of the solar wind and the corona's inner environment for decades, building sophisticated mathematical frameworks that described, with increasing precision, what the sun's atmosphere near its source should look like. And then the data arrived, and the models were wrong, not in trivial ways, not in the margins, in some of the most fundamental assumptions about the structure of the solar wind close to the sun. The data contradicted what theory had expected, with a clarity that left no room for ambiguity. The corona was doing something the models had not prepared anyone to see. This was only the beginning. Before going further into what Parker found, it is worth understanding what it was using to find it. The spacecraft carries 4 instrument suites, each designed to measure a different layer of physical reality in the solar environment. Together, they give Parker something no previous mission has possessed: the ability to simultaneously read the electric fields, the magnetic fields, the particle populations, and the large-scale visual structure of the corona, all from inside it at once, in real time. The first suite is called Fields. Its job is to measure the electric and magnetic fields threading through the solar atmosphere, the invisible scaffolding along which energy moves and plasma behaves. Like fingers pressed against a woven fabric, Fields traces the shape and tension of the field lines that organize the entire coronal environment. The second is Sweep, the solar wind electrons, alphas and protons investigation. Sweep counts the actual particles of the solar wind, electrons, protons and helium ions, and measures their velocity, density and temperature. One component of Sweep actually extends beyond the heat shield's shadow to sample the particle stream directly, its grids running red hot during the closest approaches while still transmitting data. Nothing analogous has ever been operated in the direct proximity of a star before. The third is ISOIS, the Integrated Science Investigation of the Sun. ISOIS watches the high-energy particles that solar activity accelerates to enormous speeds, particles that can penetrate spacecraft electronics and, at larger scales, disrupt satellites and irradiate astronauts. ISOIS can identify individual ion species, including helium isotopes, giving scientists a chemical fingerprint of which physical processes created the particles it measures. The fourth is WISPER, the Wide Field Imager for Parker Solar Probe. About the size of a shoebox, WISPER is the only camera on the spacecraft. It looks not at the sun itself, but sideways at the corona and solar wind, imaging the large-scale structures that the spacecraft is about to fly through before it enters them, and then correlating those images with the particle and field readings the other instruments take as the spacecraft passes inside. 4 suites, 4 perspectives on the same violent environment, and from their first encounter onward, they began revealing things no model had expected. The most striking discovery from Parker's earliest encounters was something the data showed with such overwhelming consistency that scientists initially struggled to believe their instruments were reading correctly. Everywhere, in all directions, throughout the inner solar wind, closer to the sun than any previous measurement, the magnetic field was flipping, not gradually, not rarely, but suddenly, repeatedly, at all scales from seconds to hours. The magnetic field lines that were supposed to flow steadily outward from the sun in an orderly spiral pattern were instead reversing direction, sharply, completely, and then reversing back. The same field line would point away from the sun, then fold back toward it, then point away again, creating S-shaped kinks over and over, propagating outward with the solar wind like a whip cracking repeatedly along its length. Scientists name them switchbacks. The name is descriptive. A switchback in mountaineering is a sharp reversal in a trail. a path that doubles back on itself before continuing in the original direction. The magnetic switchbacks in the solar wind behave similarly. The field line reverses, then returns. Each one is accompanied by a sudden spike in the solar wind's velocity, the plasma inside the fold moving faster than the surrounding wind, like a compressed surge pushing outward through the reversal. Switchbacks had been observed before occasionally in solar wind measurements near Earth, but they were rare there. They were historical curiosities, not dominant features. Close to the Sun, in the young, fresh solar wind just leaving the corona, they were everywhere. The dominant structure in the inner heliosphere was not the smooth, orderly outflow the models had assumed. The solar wind, close to its origin, was turbulent, kinked, and constantly folding back on itself. And here is where it gets genuinely unsettling. Scientists immediately disagree about what that means. One camp argues that switchbacks form in the solar wind itself, as Alfvén waves grow and develop through a natural instability as the wind expands outward. On this view, the switchbacks are an emergent property of how the solar wind travels, created during the journey, not at the source. A second camp argues that the data shows strong evidence for the switchbacks originating at the corona, seeded near the solar surface, and carried outward as organized structures. Field's data from Parker's sixth solar encounter showed that switchbacks appeared to align with magnetic funnels in the solar surface, suggesting a coronal origin point. Both views have supporting evidence. Neither has been conclusively established. The debate is active, published, and unresolved, which means the switchbacks are not just a discovery but a question that the data has opened and not yet closed. What is clear is that these structures appear to carry energy outward from the Sun, almost certainly contributing to the heating and acceleration of the solar wind. How much, and by exactly what mechanism, remains one of the central questions Parker's mission was designed to answer. Among Parker's most consequential early findings was the discovery of what the Alfvén critical surface actually looks like from inside. The Alfvén critical surface, named after Swedish physicist Hannes Alfvén, is the boundary in the solar atmosphere where the solar wind accelerates past the point of no return. Below this surface, the solar atmosphere is still magnetically connected to the Sun. Disturbances in the solar wind can propagate back inward, carried by waves that travel along the magnetic field lines. Above this boundary, the solar wind is moving so fast that those waves can no longer travel back toward the Sun. Material that crosses this boundary has escaped. It is no longer the corona, it is the solar wind. Before Parker's mission, this boundary was theoretical. Scientists knew it had to exist. They could calculate roughly where it should be, but they had no direct measurements from inside it. When Parker crossed the Alfvén critical surface for the first time, during its 8th orbit on April 28, 2021, at roughly 8.1 million miles, about 13 million kilometers, above the solar surface, the data immediately revealed something unexpected. The boundary was not smooth, not a clean, spherical shell surrounding the Sun at a consistent distance, the way the models had generally imagined it. The boundary was jagged, irregular, spiked with protrusions and dips that correlated with specific features of the solar atmosphere below. Parker crossed and recrossed it during a single pass, dipping below the boundary, rising above it, dipping below again, as the turbulent structure of the corona shifted around the spacecraft. Sweep data established that those spikes and valleys corresponded to coronal streamers, enormous plumes of solar material rising through the Sun's atmosphere, which had been observed from a distance for decades but never directly sampled before Parker. The boundary between corona and solar wind is not a fixed geographic line. It breathes, flexes, and folds with the dynamics of the solar activity driving it. This is not a small revision to the existing picture. The shape of the Alfvén critical surface determines where and how the solar wind is born and accelerated. A jagged boundary implies that solar wind formation is a fundamentally more irregular, patchy, and dynamic process than the smooth model suggested. And what that means for energy transport, for the coronal heating problem, for the acceleration of the solar wind, is still being worked out from the data Parker has returned. Among the unexpected findings from Parker's years of orbital data, two stand out for the particular surprise they delivered. The first concerns dust. Cosmic dust fills the inner solar system, the remnants of billions of years of collisions between asteroids, comets, and planetary debris. Astronomers had long predicted that very close to the Sun, the heat would become intense enough to vaporize dust particles before they could complete their orbits. A dust-free zone, cleared by the Sun's own thermal energy, should exist in the innermost solar system, but no spacecraft had ever been close enough to measure it directly. WISPR, Parker's camera, began detecting the dimming of reflected light as it flew closer and closer to the Sun, watching the dust thin and fade. At approximately 19 solar radii from the Sun, about 8.2 million miles, or 13.2 million kilometers, the WISPR data showed dust depleting noticeably. Models based on those observations suggest the truly dust-free zone likely begins at around 5 solar radii, roughly 2.2 million miles, or 3.5 million kilometers, from the solar surface, a region almost certainly swept completely clean by stellar heat, inside which no solid particle can survive. The second concerns solar eruptions. During its years of orbital passes, Parker Solar Probe flew through and near multiple coronal mass ejections, those violent expulsions of magnetized plasma that can trigger geomagnetic storms at Earth. Flying through a coronal mass ejection from the inside, rather than watching its effects arrive at Earth after a 2-day journey, revealed details about their internal structure that no remote observatory could capture. The texture of the magnetic fields embedded within the ejection, the particle populations accelerated in its wake, the relationship between the eruption's birth near the Sun and the storm that eventually arrives at Earth, downstream, transformed, having evolved across 93 million miles. Each piece of information from these earlier encounters was not simply an interesting fact. Each one was calibration, context, a layer of understanding built into the data before the spacecraft was sent deeper, because everything Parker learned in those intermediate passes informed what the scientists expected and expected to question when Christmas Eve 2024 finally arrived. By the time Parker Solar Probe made its final Venus flyby in November 2024 and aimed for its deepest pass yet, the scientists at Johns Hopkins were not approaching the encounter with empty models. They had years of data, years of surprises, years of watching the corona reveal itself to be stranger, more structured, more turbulent, and more dynamic than the pre-mission frameworks had imagined. They knew about switchbacks. They knew the Alphen boundary was jagged. They knew the dust thinned and vanished close in. They had watched solar eruptions from inside their own structure, and yet they also knew that none of those earlier passes had reached the depths that Christmas Eve would reach. Every previous encounter had been a step on the same staircase, but no step had descended as far as the one planned for December 24th, 2024. The data from those years of closer and closer passes was extraordinary, but it was also incomplete, and the piece that was missing, the measurements from deeper inside the corona than any instrument had ever sampled, was exactly what the Christmas Eve encounter was designed to collect. So the instruments gathered their stored commands, the autonomous systems ran their checks, mission control prepared to wait, and Parker Solar Probe fell toward the Sun, silent, alone, and carrying 6 years of scientific preparation into the most extreme solar encounter in history. Silence has a different quality when you know what it is hiding. On the afternoon of December 24th, 2024, the Mission Operations Center at the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, fell into exactly that kind of silence. The team there, engineers, scientists, flight controllers, had spent years preparing for this moment. They had built the spacecraft, guided it through 7 Venus flybys, watched it survive 21 previous solar encounters. They understood, better than anyone on Earth, what was happening in the inner solar system at that exact hour, and they could do nothing but wait. Parker Solar Probe was inside the Sun's atmosphere, moving at 430,000 miles per hour, about 690,000 kilometers per hour, flying closer to a star than any human-made object in history, following a set of stored instructions written months before, responding to whatever the corona threw at it through autonomous systems no human could override in time. The instruments were running, the shield was holding, the solar arrays were cooling themselves through circulating water in channels the width of a human hair, and no one on Earth knew any of it for certain. The geometry of closest approach meant that Parker's communication with Earth was functionally severed, not by a failure, by physics. The sun itself, its electromagnetic noise, its overwhelming radio emission, its sheer presence between the spacecraft and any antenna on Earth, made meaningful communication impossible during the encounter window. Any signal Parker sent would take minutes to reach Earth and arrive degraded. Any response from Earth would arrive long after the moment had passed. So the spacecraft worked alone. The fields instrument sampled the electric and magnetic fields threading through the corona at thousands of measurements per second, reading the invisible architecture of the solar atmosphere with a precision no telescope could replicate from 93 million miles away. Sweep's Faraday cup, the component that had to peek over the edge of the heat shield to directly sample the solar wind particles, caught electrons and protons flowing outward from the sun, recording their speed, density, and temperature at the closest distance any sensor had ever achieved. ISOIS tracked the energetic particles, cataloguing the ions accelerated by the sun's activity with enough precision to identify the specific nuclear isotopes being thrown outward, and WISPR, the camera, the size of a shoebox, positioned sideways behind the heat shield, was recording images of the solar atmosphere that no human eye had ever been positioned to see. The spacecraft was doing its work. Whether it was surviving its work was the question no one could answer until it chose to tell them. Here is what that silence actually felt like. Right now, wherever you are sitting, the air around you, the weight of your body in your chair, the quiet particular to this hour of the night, all of that is the same scale of stillness that the people at Johns Hopkins were sitting inside while they waited. Human stillness, room temperature, ordinary time, and 3.8 million miles from the sun, about 6 million kilometers, a distance that would take a commercial airliner roughly a month to cross, a machine was flying through the atmosphere of a star. The beacon tone arrived 2 days after closest approach, late on December 26th, not a science transmission, not a data stream, a single short signal, the electronic equivalent of a hand raised in the dark to confirm, still here, health confirmed, instruments intact, the wait had ended. What came next, the actual data, the measurements, the images, arrived over the weeks and months that followed, transmitted in planned downlinks as Parker swung back outward and regained stable communication geometry. Full science data requires time to extract, compress, and transmit across the interplanetary distances involved. The images that WISPR captured near the solar surface began reaching scientists in the following months, and as they did, they began to reveal something that the instruments from earlier orbits had only hinted at. The WISPR images from the Christmas Eve encounter were unlike anything the instrument had returned before, not simply because they were closer, though they were, dramatically so, representing the innermost views of the solar atmosphere any camera has ever captured, but because of what the camera happened to be pointed at when Parker passed through perihelion. As Parker Solar Probe swept through the sun's atmosphere on December 24th, a coronal mass ejection erupted from the sun. A coronal mass ejection, CME, is one of the most violent events the Sun produces, a sudden, enormous expulsion of magnetized plasma, billions of tons of charged material flung outward into the solar system. These are the events that drive the most severe space weather at Earth, the events that in 1989 took down the Quebec power grid in 90 seconds. And Parker was inside the solar atmosphere when it happened. WISPR recorded the eruption, not from a distance, not from a vantage point at Earth orbit, not from the perspective of a spacecraft in the relative safety of the outer solar system, watching through a telephoto lens, from inside, from within the corona, looking at a CME as it was actively forming and erupting at scales of detail no previous instrument had been close enough to capture. What the images showed in the CME's wake was something that stopped scientists. After the CME erupted outward, after that massive expulsion of magnetized plasma began its journey across the solar system, WISPR continued watching the space behind it. And what appeared in that space was not what the models predicted. Elongated blobs of solar material were falling back toward the Sun. Not all the material ejected in the CME had escaped. Some of the magnetic field lines released with the eruption did not extend outward and carry material away. They lingered, they stretched, strained against the pull of the magnetic field anchored to the solar surface, and then slowly recoiled, pulling blobs of solar plasma back inward with them, back toward the Sun, in what scientists described as inflows. This phenomenon had been glimpsed before, from a distance, with instruments like SOHO and STEREO operating at or near Earth's orbit. Scientists had seen hints of material falling back toward the Sun, but those were distant observations, like watching rain fall from inside a building and seeing only the general movement through a far window. Parker's images were taken from inside the corona itself. Angelos Vorlidas, WISPR project scientist at the Johns Hopkins Applied Physics Laboratory, described what the images revealed. Some of the magnetic field released with a CME does not escape. Instead, it lingers and eventually returns to the Sun, recycled back into the solar atmosphere, reshaping the magnetic landscape in the process. Think about what that means for a moment. We have been building models of CME behavior for decades, models that inform space weather forecasts, models that attempt to predict where a solar eruption will travel across the solar system, whether it will hit Earth or miss, how strong its effects will be when it arrives. Those models treated a CME as largely a one-way process. Material erupts, material escapes, material travels outward. But what the Christmas Eve data showed is that the process is not purely one-directional. Some material comes back, and as it does, as those inflows contract back toward the solar surface and drag blobs of nearby plasma with them, they interact with the magnetic fields swirling beneath. They reconfigure the magnetic landscape of the region from which the CME erupted, and that reconfiguration can subtly alter the trajectory of any subsequent CME that forms in the same region. Vorlidas put the implications directly. The magnetic reconfiguration caused by inflows may be enough to point a secondary CME a few degrees in a different direction. A few degrees, a difference that sounds trivially small. But at the scale of the inner solar system, a few degrees of angular difference is the margin between a CME striking Earth head-on and sweeping past it entirely. That is enough to be the difference between a catastrophic geomagnetic storm and an aurora. What makes the Christmas Eve encounters data so consequential is not any single observation. The WISPR images of inflows and CME dynamics are extraordinary on their own, but the encounter's value comes from the simultaneous operation of all four instrument suites. WISPR, seeing the large-scale structure of what was happening, while Fields measured the magnetic field configuration threading through the same region, while SWEAP sampled the particle populations within the same eruption, while ISOIS tracked the energetic particles accelerated by the same event. No camera working alone could have produced what the Christmas Eve data produced, and no particle and field instrument working alone could have connected what it measured to the visual structures WSPR was photographing. The power of Parker Solar Probe as a scientific instrument is not in any one of its components. It is in the convergence of all four, operating simultaneously from inside the environment they are studying, at closer range than anything that came before. The resulting picture of what happens when the sun erupts, the close-range imaging, the direct particle measurements, the magnetic field configuration, the energetic particle spectra, is the most complete cross-sectional portrait of an active solar eruption ever assembled, and it is already being incorporated into the models that space weather forecasters use to predict the impact of solar events at Earth, the Moon, and Mars. Parker Solar Probe was not simply a survival experiment. The Christmas Eve 2024 encounter was a scientific transformation, from 6 years of increasingly close preparation to the deepest, most detailed measurements of the solar atmosphere that science has ever obtained. Noor Rawafi, Parker Solar Probe project scientist, described the result plainly. The spacecraft had transported humanity into the dynamic atmosphere of the closest star to Earth at a level of detail never previously possible, not from a distance, not with inferred measurements, from inside. But now the question that has been waiting since the beginning of this journey demands an answer. The corona heats itself by unknown mechanisms. The solar wind originates in its fires. Switchbacks ripple through it like folds in an invisible current. The Alphen boundary is jagged and dynamic. CMAs that we assumed traveled cleanly outward actually recycle portions of themselves back into the solar atmosphere. The magnetic landscape of the sun reshapes itself between eruptions in ways our models have not accounted for. Parker Solar Probe found all of this from inside, and every single piece of it connects directly to the world you're living in right now, to the satellites that tell your phone where it is, to the power lines that bring electricity to your home, to the communication infrastructure that ties the modern world together, to the astronauts who will eventually travel to the Moon and Mars through the same solar wind Parker has now mapped from its birth. None of this is philosophical. The sun's reach is not limited to sunlight and warmth. The sun's atmosphere, the corona, extends outward across the entire inner solar system. We have always lived inside it, whether we understood it or not. Parker Solar Probe has now made it possible to understand it with a precision that no previous era of science could achieve. What remains is the final question. What does all of this actually change? For the models, for the forecasts, for the future, for humanity's ability to understand not just our sun, but every star in the universe, seen through the lens of the one star close enough to study from inside its own atmosphere. The answer is both more grounded and more profound than most people expect. The question at the heart of this mission was never purely scientific. It was never purely about the coronal heating problem, or the Alphen boundary, or the switchbacks, or any other specific phenomenon that Parker Solar Probe measured from inside the sun's atmosphere. Underneath all of it, beneath the physics and the engineering and the 60-year arc from a rejected paper to a spacecraft inside a star, the question was always about this. Can we understand the sun well enough to protect ourselves from it? And the answer, after nearly 7 years of data, is yes. Not completely, not permanently, not without further work, but measurably, meaningfully, consequentially, yes. What Parker Solar Probe found inside the corona has already begun to change the models that space weather forecasters use to protect the infrastructure that modern civilization depends on. The understanding it carried home from inside the atmosphere of a star is already at work, quietly, in the software that monitors the solar environment and tries to tell us what is coming. Let's put this in perspective, not the perspective of solar physics, but of the world you wake up in every morning, the GPS signal that routes emergency vehicles to accidents, that guides aircraft through clouds, that tells a fishing boat where it is in open water. That signal travels from satellites orbiting in an environment continuously bathed by the solar wind. During a major geomagnetic storm, GPS accuracy can degrade so severely that navigation becomes unreliable. For most daily navigation, this is an inconvenience. For a surgical procedure guided by imaging, for an aircraft making an instrument approach in fog, for a hospital dependent on precise timing signals, it is something else entirely. The power transmission infrastructure of every industrialized nation on Earth runs through long conductors, cables, pipelines, transformer connections that act as antennas for the geomagnetically induced electrical currents that strong solar storms drive through the ground. The 1989 Quebec blackout lasted 9 hours. A study conducted for the United States Federal Emergency Management Agency estimated that a storm of the scale of the Carrington event, the most powerful geomagnetic storm in recorded history, which struck Earth in September of 1859, could affect power grids across wide regions of North America and Europe simultaneously, with restoration timelines measured not in hours but in weeks or months. The Carrington event happened before the electrical grid existed, before GPS, before satellites, before fiber optic communication cables routed across ocean floors. The world that a Carrington-scale event would strike today is incomparably more dependent on electromagnetic infrastructure than the world it struck in 1859. And today, the primary warning system for incoming solar storms relies on satellites positioned between Earth and the Sun at a location called the L1 point, roughly 900,000 miles, about 1.5 million kilometers, sunward from Earth. Solar wind takes roughly 15 to 60 minutes to travel from that point to Earth. That is the warning window. 15 minutes to an hour, depending on storm velocity, to alert power grid operators, satellite managers, aviation coordinators, and emergency services that a solar storm of uncertain intensity is about to arrive. That is the problem Parker Solar Probe was built, in part, to address. Here is what most people misunderstand about space weather forecasting. The models that predict whether a solar eruption will strike Earth, how intense its effects will be, and when exactly it will arrive, are built on measurements taken far downstream from the event's origin. The L1 monitoring satellites read the solar wind after it has already traveled 93 million miles, after it has expanded, cooled, evolved, and in some cases interacted with other solar wind streams that departed earlier. By the time those instruments measure a storm, it has already undergone roughly 22 hours to 2 days of evolution since it left the corona. Predicting a hurricane from a weather station that only receives data after the storm has already crossed an entire ocean is fundamentally limited. The structure of the storm at origin, the details that determine its ultimate intensity and direction, have already been partly erased by the journey. Parker Solar Probe measured the solar wind and solar eruptions close to their birth region, not after 22 hours of evolution, hours after eruption, sometimes during eruption, from inside the corona where the structure of the event was still largely intact. The data from those measurements, the magnetic field configuration of a CME while it is still forming, the particle populations while they are still being accelerated, the initial trajectory and velocity before solar wind interactions have altered them, provides the starting conditions for a model rather than a downstream snapshot. A better starting condition produces a more accurate prediction. The inflow discovery from the Christmas Eve encounter makes this concrete. Knowing that magnetic material from a CME can fall back toward the Sun and reconfigure the local magnetic landscape, subtly redirecting subsequent eruptions, adds a layer of complexity to the models that was previously invisible from the L1 vantage point. A secondary CME emerging from an already reconfigured region may travel in a slightly different direction than a naive model would predict. A few degrees of angular difference, enough to determine whether it strikes Earth or misses entirely. That margin is now in the models. But here is where the mission's implications reach beyond forecasting, beyond the practical, and into the genuinely profound. The sun is the most studied object in the history of science. Every civilization that has ever existed on Earth has watched it, measured it, tried to understand it. In the modern era, we have aimed every form of instrument at it: spectroscopes, coronagraphs, X-ray telescopes, radio receivers, satellite imagers. Entire research programs across multiple countries have been devoted to understanding the sun's behavior and predicting its outputs. The literature of solar physics spans more than a century of published observations, and yet what Parker Solar Probe found when it finally entered the corona, from inside rather than from 93 million miles, revealed that nearly every model built from that external vantage point was working with a simplified, smoothed out, averaged version of the actual solar atmosphere. The Alfvén boundary was not the smooth spherical shell the models assumed. The solar wind near its source was not the orderly outflow the models described. The CMEs that models treated as simple outward-flowing events were partly recycling material back into the solar atmosphere in ways that reshaped subsequent eruptions. The models were not wrong in the way that pseudoscience is wrong. They were incomplete in the specific way that any measurement taken from the wrong distance is incomplete. You can describe a painting from across a room and be entirely correct about its colors and composition. You can also miss the brush strokes that explain how it was made. Parker flew close enough to see the brush strokes. What it found was not a calmer, simpler sun that our models had exaggerated. What it found was a sun more structured, more dynamic, and more physically active at fine scales than the models had been able to resolve. The corona heats itself through a combination of processes: magnetic reconnection releasing burst energy, Alfvén waves depositing energy as they propagate upward, turbulence converting the churning motion of plasma into heat. And those processes are not uniform, not smooth, not operating on a steady background. They are patchy, intermittent, and organized along the jagged geometry of the sun's magnetic field. The question of which process dominates the coronal heating, the question that has remained unresolved for nearly 90 years, is still not conclusively settled. Parker has not delivered a single clean answer, but it has, for the first time, delivered measurements from inside the region where the answers live. The data is already narrowing the range of possibilities. The models are already being revised, and the revisions are bringing them closer to what direct measurement shows is actually happening, rather than what distant observation allowed us to infer. That is what science looks like when it works at its best, not the moment of final resolution, the progressive narrowing toward truth. Let's state it plainly, because it deserves to be stated without abstraction. Parker Solar Probe found a corona that is dynamic, magnetically structured, and continuously active. In ways our models underestimated, it found solar wind forming in a patchy, irregular process governed by a jagged Alfvén boundary that breathes and shifts with the sun's activity. It found switchbacks, sudden magnetic field reversals, as the dominant structural feature of the inner solar wind, almost certainly carrying energy outward from the corona and likely contributing to both wind acceleration and coronal heating, through mechanisms that are still being disentangled. It found CMEs that do not fully escape, that recycle portions of their magnetic material back into the solar atmosphere, reshaping the magnetic landscape and potentially redirecting subsequent eruptions. All of these findings are published. All of them are now being incorporated into the models that protect our technological civilization from the sun's most disruptive outputs. And Parker Solar Probe continues. The primary mission, which ended in 2025, included 24 solar orbits shaped by 7 Venus flybys. Parker Solar Probe will remain in its current orbit around the Sun, which brings it within 3.8 million miles of the solar surface, and continue making observations. Parker Solar Probe remains in excellent health, with both the spacecraft and its instruments ready to continue their groundbreaking mission. The spacecraft has already completed its 27th close approach to the Sun in March 2026, gathering data as the Sun moves through an active phase of its 11-year cycle. Every additional orbit adds measurements. Every additional measurement sharpens the model. Every sharpened model improves the forecast. The machine that Eugene Parker watched disappear into a pre-dawn Florida sky in August 2018, knowing it would never come back, is still circling the star whose existence it was built to investigate, still working, still sending data home across the distance it cannot cross in the other direction. Beyond space weather forecasting, Parker's mission carries an implication that extends far beyond our own solar system. The Sun is the only star in the universe that we can study from inside its atmosphere. Every other star we have ever observed, the 100 billion in our galaxy, the trillions across the observable universe, we have observed only from the outside, reading the light they emit across distances that strip away all fine structure. What we know about stellar physics, stellar winds, stellar coronae, stellar magnetic activity, all of it rests on theoretical models built primarily from observations of our own Sun, viewed from a distance that, until recently, prevented us from accessing the physical processes that actually drive those phenomena. Parker Solar Probe is, in the most direct sense, humanity's laboratory for understanding stars, not just our star, all of them. The mechanisms it measured inside the corona, the wave propagation, the reconnection events, the particle acceleration, are almost certainly operating inside every stellar atmosphere in the observable universe. The findings that reshape our model of the Sun's corona will reshape our understanding of stellar corona everywhere, across all types and ages of stars, across distances so vast that no instrument will ever reach them directly. We studied one star from the inside, and in doing so, we learned something about all of them. We have travelled a long way tonight, from a Christmas Eve morning in 2024 through the history of a rejected idea that became a foundation of modern physics, through 7 years of orbital mechanics and carbon foam and autonomous systems and silence, through switchbacks and jagged boundaries and solar material falling back toward the Sun it could not escape. You came here not knowing what a coronal mass ejection was, or why the Sun's outer atmosphere is hotter than its surface, or why reaching the closest star is the hardest journey in the solar system to make. And now you know something that most people alive today do not know, not because it is secret, but because no one has taken the time to explain it clearly, the way it actually happened, with the weight it actually deserves. That is not a small thing. At the start of this journey, a small machine sat alone between us and the star, translating proximity into understanding in ways no telescope on Earth could replicate, carrying the question inside the atmosphere of a star, surviving where? Nothing had survived before. Parker Solar Probe cannot come back. Eugene Parker understood that when he watched it go. Knowing it will never come back, he said, a machine that disappears into the night sky and does not return. But what it found has already crossed the distance. The understanding arrived, and the machine is still out there, circling, measuring, sending signals back across 93 million miles to a team of people at a laboratory in Maryland who built it, guided it through 7 planetary gravity assists and 26 close approaches to a star, and who are still listening to everything it has to say. Humanity did not conquer the Sun. It never could. The Sun remains older than the Earth by nearly 50 million years, and will outlive it by several billion more. Its energy output in a single second exceeds everything the human species has produced in its entire existence. Its corona extends outward past every planet we have ever visited, wrapping the entire solar system in an invisible magnetic environment that we have lived inside without fully understanding for the whole of our history. Parker Solar Probe did not change any of that. What it changed is our position within it. We went from the outside to the inside, from inference to measurement, from the downstream approximation to the source. We did not make ourselves larger. We made ourselves more careful, more precise, more honest about what we actually know and what we are still learning. The sun remains vast, but no longer entirely unreachable, and in that distance closed, in the 4.5 inches of carbon foam between 2,500 degrees and 85, in the single beacon tone received 2 days into silence, in the switchbacks and inflows and jagged boundaries that no model anticipated, we did not conquer the star that has governed every day of every human life that has ever been lived. We listened to it more closely, and in the quiet that follows a long journey, there is something worth sitting with. The fact that human curiosity, given enough time and patience and engineering and courage, can reach even here, inside the atmosphere of a star, reading the magnetic brushstrokes of the corona, sending the data home, touching the sun to understand how to live beneath it more wisely. For 4.5 billion years, the sun has been reaching toward you, its light across 93 million miles of silence, its solar wind flowing through the space your planet moves through every single day, its invisible atmosphere stretching outward past every orbit, wrapping the entire solar system in something you have always lived inside without ever knowing it. For all of that time, every morning that ever rose, every civilization that ever watched the sky and wondered, the reaching only moved in one direction, until Christmas Eve, 2024. That morning, something we built entered the sun's atmosphere, measured it from inside, listened to it from a distance no instrument had ever closed before, and for the first time in 4.5 billion years, the reaching went both ways. That is what tonight was about. Not just the engineering, not just the physics, but the oldest impulse there is, to close a distance, to say, across whatever space exists between you and something ancient and vast and powerful, I am here, I can feel you, I wanted to understand you, you stayed with this tonight, that means something. If this journey was worth your time, a like and a subscribe are how you tell me. More are coming, quieter ones, stranger ones. I hope you will be there. Thank you for making it this far. Sleep well tonight. You were never as far from the sun as you thought.